groundwater quality. All right. Now, if you'd mentioned that at a meeting, 20 years ago, people like the United States Environmental Protection Agency, they would have your neck if you mentioned anything like that. But even they have changed their minds and have admitted that groundwater dilution is a mechanism for attenuation, that it is a viable one. What else? In the middle here is a monitoring well. All right. When you see typically in diagrams these lines here, this is the open interval that's open to the groundwater. The groundwater flows into this, and then we pull a sample out for analysis, and here's a fellow doing something like that. All right. This is what I was getting at this morning. I would bet they're going to have a monitoring program, even though it makes little sense because of the long period of resaturation. I bet it is so easy for the government, the Swedish government, to impose a groundwater monitoring program. If nothing else, because people will expect it. I say that because for years I worked on a carbon sequestration project, geological carbon sequestration. We were injecting, we still are, carbon dioxide to a depth of 5,000 feet. But we still had to go to people's homes and collect tap water and analyze it and give them a report once a month to clearly show them your drinking water's fine. It's not been contaminated by any of what's going on at this facility. Even though we as scientists knew it was impossible for groundwater to affect them. But it was required. It was required as a monitoring program. That's why I would bet that for Forsmark, they'll have a monitoring program. Anyway, that was an aside. Attenuation mechanisms. Diffusion. Spontaneous movement of radionuclides or any molecule from an area of greater concentration to that of a lesser concentration. Diffusion will occur if there is a concentration gradient, according to the second law of thermodynamics, which is the outcome being entropy increases. As things spread out, entropy increases. At some molecular level, nothing is completely impermeable. I hear this a lot, an impermeable barrier. Nuts. This table is not impermeable. Ouch. It is to my hand, but at the molecular level, molecules can still diffuse through it. All right? You can have diffusion through waste packages, through the copper canisters. Whether they've corroded or they're intact, you will still have diffusion through the copper canisters, diffusion through the bentonite, diffusion into the granite. Okay? Let's see. Steel drums, canisters, ceramic vitrified waste forms, diffusion from disposal sites. No one is immune from diffusion. Movement through compacted clays, soils, rock formations. Movement in groundwater, even if the water itself isn't moving, you can have diffusion.
Question. Isn't the groundwater moving in this case? It's moving down?
Depends on the gradient.
Yeah, but I mean...
For a lot of times, yeah, from higher to lower gradients, if it's moving at all. Groundwater in a lot of these deep scenarios hasn't been moving for millions of years. It's stagnant. It's at the bottom. Now, the reason diffusion isn't a major player is it's pretty darn slow. The rates of diffusion tend to be on the order of centimeters per years. So even though we do have diffusion from waste packages, they tend not to travel very far, very quickly. Of course, the only concern is if you have diffusion that moves a radionuclide from such a source into a scenario where advection is actually carrying the contaminants faster, then we potentially have a problem. But I just wanted to add this to your list. In unsaturated and saturated flow, like I mentioned, dilution, dispersion. Dispersion is spontaneous physical spreading of both water and air. It occurs, again, in response to the second law of thermodynamics. We have water-air partitioning. I learned this as Henry's law, which is the vapor phase concentration is equal to a Henry law constant times the solubility of the constituent in water, whether it's a radionuclide, as far as an ion or a gas, the solubility in water. There aren't too many radionuclides we worry about this kind of air-water partitioning other than radon. Chemical reactions. Precipitation dissolution reactions. As I'd mentioned, I think earlier in one of my lectures, if we have strontium-90, all right, if we have enough naturally occurring sulfate, say from the oxidation of pyrite, iron sulfide that's naturally occurring, say in the bentonite or somewhere within the granite, and it oxidizes, mixes with air. If we have enough sulfate, then we can have strontium plus sulfate, and it can precipitate as a strontium sulfate. The mineral form of this is called celestite. That's about what it looks like. All right. I've got a big chunk of celestite in my collection that I've had for many years. That's not it, but you get the idea. So how this is expressed is strontium-90, the thermodynamic activity of it, if that means nothing to you, we'll say concentration. The concentration of strontium times sulfate is equal to an ion activity product, IAP. At equilibrium, chemical equilibrium, where the forward reaction is the same as the reverse reaction, right? You got that? Okay. The IAP is equal to the reaction constant, KT. Okay? When the IAP is greater than the reaction constant, then this chemical, celestite, should precipitate out of solution. In other words, there's more in solution than there should be. And as the solution equilibrates, then celestite will precipitate out of solution until the ion activity product of strontium and sulfate is equal to the reaction constant. And if you haven't guessed, the reaction constant is measured at equilibrium. So that gives us a basis for comparison between equilibrium conditions and non-equilibrium conditions. When the ion activity product is less than the reaction constant, celestite dissolves, if it's there. If it's there. If it's not there, nothing happens. And strontium continues to transport, unabated by chemical precipitation. All right? We with me so far? Good. Ion exchange. This is exchange between ions in solution with those on a stationary phase. For those of you, I think we've got a few chemies, chemical engineers. This is a process used to purify chemicals and decontaminate liquid samples. Right? My chemical engineers? Yeah? Okay. Best example I can think of, ion exchange resin. Ion exchange resins are used to decontaminate contaminated solutions, such as in the decommissioning of nuclear power plants. Simply put, if you let the little orange circle here represent this, these are very, very small glass beads. What we do then is we coat the glass beads with hydrogen. And then in this case, let's say we want to clean up a solution with cesium. Well, we add cesium, and by a mass action effect, we put cesium on the glass bead and exchange that with the hydrogen. And the hydrogen goes into solution. So now we have an acidic solution, but it doesn't have the same cesium. Okay. And in practice, once we have used up the capacity of this resin to clean up cesium, then most likely it would be disposed of as a low-level waste. Ion exchange occurs in nature, going back to our geologic repository. Soils, clay minerals, and soil organic matter can remove ions from solution by ion exchange. And this is a big deal. Very important in other applications such as agriculture. Ion exchange is a type of adsorption reaction. I tend to use the word sorption because, well, I'll explain it this way. When we say adsorption, we're saying specifically that we know it's a surface phenomena. Sometimes we don't. If we're not sure if there's a degree of some other processes that I'll explain in a little bit, we just call it sorption, to be on the safe side. Let me explain. Surfaces of clay minerals often have a negative charge resulting from isomorphous substitution within the clay structure. This is something I was trying to say in another lecture. By and large, when you go out there in the real world, most natural geomedia has a negative charge on it. And that's why cations, positively charged ions, are sorbed. Positively charged anions are not and tend to be more mobile and skip along like iodide. Going back to the clay structure. Here we have the structure of illite, which is a common clay mineral. And you know what state in the United States illite is named for? Illite. 498 students, illite. Say it.
Indiana.
Where went your grade?
Illinois.
Illinois! Where it was first described and named. All right, by isomorphous substitutions, I mean that within the octahedra, you've got silica and aluminum, shown by these purple guys. Sometimes you have other guys creep in there, like iron and manganese. There's other cations that can fit into the lattice physically, but they don't have the same valence. So the overall effect is they create a negative charge on the external part of the clay. Well, nature doesn't like a vacuum any more than she likes unbalanced electrical charges. So what does a clay mineral do? It will adsorb or sorb positive ions to balance that charge so that it's happy again. That's how it works. Like I said, cations are concentrated on the surfaces to balance negative charge. Hence, the cation is removed from solution and it is immobilized. So if we have a cation that has escaped from a repository, then nature has the capacity to absorb it, take it out of solution, and the game is over. And that's a good thing. Natural organic matter in soil also has positive and negative functional groups. They have a lot of organic sites, hydroxyls if you will. And these hydroxyls can protonate and deprotonate depending on the pH of the solution they're in contact with. So you can have sites that have a positive charge and sites that have a negative charge. Very versatile. Very versatile. But not so common in things like granite. Absorption of radionuclides cannot be predicted a priori, that is from theory. We don't have any theories that are that good. They have to be measured experimentally. All right. Now, I had the impression Patrick was kind of dismissing the work needed to measure absorption. I didn't quite understand that. It's not that much work, and it can be so essential to doing an assessment, an environmental assessment, safety assessment on any kind of scenario where you need that kind of information. So ignore what he said. All right. The experimental results are usually generalized as a sorption isotherm, which is a plot of the amount sorbed versus the equilibrium concentration. Right? It's a property that is measured at equilibrium. That is, again, the rate of change with respect to time has ceased. All right. Here's what an isotherm looks like. An example. Here you have uranium-6 sorbed on quartz. Now you wouldn't think quartz is very reactive. Typically it isn't. But here's an example just to show that it can be. Here's uranium-6 in solution as microgram per liter. These are the equilibrium concentrations. And these individual points represent points that were measured in a laboratory at chemical equilibrium. Now you see there's a line drawn through them. That is a statistical regression. Really, an isotherm is a statistical regression. And that will be part of the problem for the material for question 4, which I'll explain at the end of the lecture. In this particular example, they measured at pH 6, 6.5, 7.1. They're kind of looking at the impact of pH on the absorption of uranium by quartz. I mean, in practice, what you do is you might add an acid or a base to that pH. All right, then you mix it up, then you open it and readjust it and mix it up. It's very tedious. It's very tedious. For my PhD project, I did about 1,400 absorption measurements. Took me forever. Could do them in my sleep. Now, if the absorption isotherm is linear, then the data can be generalized by a simpler expression. K over M is equal to KD times C. And this KD is the term that Patrick threw out at you, but he didn't really put it into a context. X is the mass absorbed. That is the mass of the radionuclide. All right. M is the mass absorbent. Could be a clay, the quartz in the previous example, whatever, the rock or the clay or whatever it is we're really interested in studying. The KD is a partition coefficient or an absorption coefficient. All right. In environmental studies, KDs are marijuana. Everybody wants a good KD for their system. All right. And sometimes it's difficult to find KDs for their particular system that are valid. But that is something a lot of we search for, we seek and want. And of course, in this case, C is the concentration, mass over volume, the concentration of the radionuclide, or whatever it is we're interested in. Now, these partition absorption coefficients, they give an idea about the mobility of a radionuclide in subsurface environments, which is of paramount understanding. We're trying to make like a safety assessment. Now, if we have a KD of 0, there's no retention. Right? That means that constituent is basically moving at the same rate as the groundwater because it's not being retained, it's not being absorbed. And shown here in orange or in yellow for emphasis, in general, anionic radionuclides are more mobile than cationic radionuclides. So, right off the bat, it's really good to know if you're concerned about a radionuclide in solution, does it occur as a cation or an anion? Just that knowledge, that simple knowledge, is a really good indication of a problem or not so much a problem. All right, just right off the bat, if you know that much, just based on this simple relationship. Now, Patrick was right. Measuring KDs in a lot of situations is expensive. Sometimes the expense has to do with the analytical determinations if it's something a little different. If you're like measuring KDs of specific isotopes, for example, all right, that's expensive. What's been made available are such things such as this. These are default KDs used in modeling studies. These were generated from Argonne National Laboratory's user manual for RAD version 6. Right. This is a model that you can acquire, not that cheap, that you can do assessments of the transport, the fate and transport of radionuclides depending on whatever scenario you have as a job. So if you can't afford to measure KDs, these are default values that you can use. Let's discuss some of these. All right. Let's start with strontium here. Has a KD of 30, all right, suggesting that there would be some element of absorption. Whereas, let's look at technetium. In this particular case, they give KD a technetium of 0, technetium a KD of 0. In other words, no retention. We'll put that on hold for a second. Cesium 500, iodide 0.1. Radium 70, thorium 60,000. So that would suggest thorium is pretty darn immobile. Now, A little insight, thorium is also pretty darned insoluble. Hard to get a lot of thorium in the solution. It's much happier precipitating as a carbonate or a hydroxide. Neptunium 0, plutonium 2000. Hey, remember we're all worried about plutonium. The magnitude of this default KD would suggest what? It's not very mobile should it escape a repository. That's potentially a good thing to know. At the same time, here's americium 20. It would be relatively 2 orders of magnitude more mobile. Okay? Here's an isotherm that I constructed. On the x-axis is the solution concentration, microgram per liter, and this is the amount absorbed in microgram per kilogram. Again, microgram of either plutonium, cesium, and technetium versus per kilogram of whatever the sorbent is. All right. There's a couple things to take home from this graph. If you notice here, in this particular situation, technetium is shown as a technetium oxide. See the little mark there? Is an anion. Remember the default KD for technetium was what? 0, okay? Which implies it would not be absorbed. Well, this isotherm conforms to that expectation in that it's pretty much a flat line that hugs the x-axis. Despite whatever concentration, nothing is absorbed. No significant absorption. Now, if we look at cesium, in this particular case, cesium occurs as a +1 cation. And as you can see, there's an element absorption here because it is a +1 cation. Plutonium is a +3. You have greater absorption because you have a greater electrostatic interactions between the ions and the negative surface of the clay or the soil or whatever it is we're talking about. So that's another take-home message. If an ion has greater charge, such as this guy here, it's going to be less mobile. Just simply because there's a greater opportunity for these electrostatic interactions. Okay? How does this KD relate to anything in the real world? Well, we start with the term retardation. This is about the only application I can think of where that word is still politically correct. This is the only place you can use that word anymore. But anyway, retardation is the velocity of groundwater divided by the velocity of the radionuclide. Now, the retardation term, R, is equal to 1 plus this guy. This is the dry bulk density of our geomedia, whatever it should be, times KD, right there, divided by the volumetric water content. Okay? With me so far? This is kind of a back-of-the-envelope type of calculation. If we ignore dispersion and we just don't want to use a fancy computer, this is something you can do with a calculator, which I've done here. If we want to talk about the distance traveled, we use this simple expression. T is time. Ksat is the saturated hydraulic conductivity. There was a bit of discussion about that this morning here, wasn't it? It's just simply a number that tells you how quickly water moves through material, albeit soils, sands, whatever. It can be measured in a lot of different ways. We won't worry about that for now. I is a hydraulic gradient, which of course is the force that pushes the water through the geomedia. Ne, the water conducting porosity. That's a little harder to describe. We've been talking about porosity as the space between the particles. When we talk about the water conducting porosity, we're actually talking about that volume of the total porosity that water can actually move through. Like if you have two particles that are close together intimately, that creates a dead end. Water could flow into there, but it ain't going anywhere. That's as far as it's going to go. So the water conducting porosity is kind of a guess on how much the total porosity is really capable of transmitting fluids from one place to another.
One question. And the air? What is the air? before the NE.
I?
R.
R.
Yeah. Yeah, the retardation.
I'm sorry, sir.
No,
You're good?
Yes, it's the retardation.
Okay. All right, all right. Anyway, coming up with a number for water conducting porosity is a bit of a guess. A lot of times we'll take total porosity and use half of that, 30% of that. The trick is it won't make that much difference. But measuring experimentally is a challenge. But in practice, it tends not to really be that big a deal. Give you an example. Suppose we're talking about the movement in sand from a leaking tank. All right, I chose sand because it's kind of a simple material. Let's let the dry bulk density be 1.7 grams per cubic centimeter. Let's say the volumetric water content is about 0.3 cubic centimeters per cubic centimeter of sand. Let's say that the hydraulic conductivity is 10 to the minus 3 centimeter per second, which is a good number for sand. Let's impose a gradient of about 0.1 centimeter per centimeter, and let's take a shot in the dark that the water conducting porosity is about 0.3. Again, like I said, it won't matter that much. If you take those numbers and plug them into the previous equation, you get this. All right. For example, if we had radium or tritium dissolved in the water, the KD of tritium is 0. So it moves just as fast as the water because, among other things, chemically it's indistinguishable from water. Tritiated water, it behaves chemically just like ordinary water. So R becomes 1. And in this case, in 30 days, it would have moved about 8.5 meters. Okay? So that's kind of a baseline for comparison. Technetium. Remember, we used a default value of KD of 0. So technetium did the same thing. It moved 8.5 meters in 30 days. Now cesium did not have a KD of 0. All right, it had a larger number. In this particular example, the KD was about 2,800, and it only moved 2 centimeters. Lead had an even larger KD, and under the same conditions, it moved half a centimeter. So, KD makes a big deal. It makes quite a difference. When you consider the water moved 8.5 meters, and plutonium moved about that far in the same amount of time. Make sense? Therefore, we can conclude with some confidence plutonium and cesium are not going to be very mobile when compared to groundwater. You know where I'm going with this. We've had groundwater, it's breached the disposal area, it's leached contaminants from our copper canister, but still, under certain conditions, it's not going very far. It's not going very far quickly. And for that, we can thank the retardation term, which of course is based on absorption. All right? You with me? Excellent. Reduction, oxidation reactions. Let's see. These are chemical reactions in which the valence or oxidation state of a radionuclide is changed by either adding or removing an electron. That's all it is. I wish in freshman chemistry they would just say it that way, but they don't. They have to say something else. Chemically reduced systems are typically oxygen poor, such as deep groundwater. And of course, I think that's been a subject, that's been something we've mentioned in a couple different lectures already. Now, a reduction, oxidation reduction example. Let's say under oxidizing conditions, technetium occurs primarily as technetium O4 as an anion, technetium 567, which is a mobile ion, giving a KD of 0. But under reducing conditions, it's different. It's a different way. Under reducing conditions, technetium occurs as technetium 4, which precipitates as a solid phase. That's the classic example of how redox makes a difference. Under reducing conditions, technetium is much happier to precipitate and not move, just because we have a difference in the valence from technetium one form to another. Okay? So that's a good example of why redox chemistry matters. We've seen a few EH-pH diagrams. This one is annotated perhaps with a few more details to give you kind of a way of comparing what I'm talking about, the numbers, with some sort of physical natural analog. This lower line is the chemical stability of water. Below that, we're reduced into hydrogen. The upper line is the chemical stability of water here, and above that, we oxidize into oxygen. So we really want the stability field between the two. So in the most oxidized systems, these are in contact with the atmosphere. Well, that makes sense. They're closer to atmospheric oxygen. Oxygen dissolves into the water. They would be the most oxidized. But like for our geologic repositories, we're really thinking about down here, groundwater that's far removed from the atmosphere. It will be more chemically reduced. I don't know if some of the speakers mentioned it or not, but there are situations where the groundwater in a deep geologic basin, it hasn't been part of the hydrologic cycle in millions of years, and probably never will be again. Let's see here. And that's all we need from this, I think. All right, let's look at an EH-pH diagram for plutonium, because there's a lot of stuff here. For example, in this area here, over a large range of EH, but in relatively acidic systems, what this diagram shows, this is the most thermodynamically stable form of that constituent, in this case plutonium. It's not to say all the plutonium occurs as that form, but this would be the dominant form. As you can see, the dominant form here is plutonium 3+, which is what we used in that example with the isotherm. It absorbed readily. Now, if we look at pH and go in the direction from an acidic solution to, let's say, a moderately alkaline solution, all right, you can see the dominant form here is plutonium oxide. AM means amorphous. That is to say, it doesn't have a definite chemical structure, say, to X-ray diffraction, which is one way of defining amorphous forms from those that have crystallinity. For us, doesn't matter so much. The point is, it precipitates. It's gone. It's not going to move anymore because thermodynamically, it's happier to be a solid phase and precipitate out of solution just because we've changed the pH of the system. If we look at something here close to neutral pH but highly oxidized, you can see we have a plutonium oxide, a cation, monovalent cation here, and then there are a number of other more exotic things that kind of go outside the stability of water but are included for the sake of completeness. All right? So you with me so far with the pH-EH diagram? Cool. Sir? Shoot.
Is it in previous slide?
Huh?
Is it related to plutonium concentration or solubility? Is it this diagram?
Yes.
So what if, in general case, I want to show the public or make some graph with these things?
Okay. This shows the thermodynamically most stable form of plutonium. It doesn't tell you anything about rates of reaction or concentrations. That you have to tack on additional information. This just gives you a way of anticipating, what do I do next? Where do I go from here? What do I have to be concerned about? Now, in a particular situation, then yeah, you'd start looking at concentrations, and frankly, I don't know your situation, but I would do chemical modeling to really nail down whether it's going to precipitate, dissolve, or other. Is it going to combine with other ligands like chloride and hydroxides and carbonates to get a much better picture? Yeah, that's a good point. These figures like this one are not based on, ouch, multi-component systems. Like we haven't dumped in all sorts of chloride or sulfate or something, which could change the outcome of the figure. All right. So these are just kind of boundary conditions. It just, like I said, it's a tool to tell you where should I go from here. All right? It's not the be-all, end-all, no. All right, next. Talk about the fate chemistry of plutonium. That is, its fate in the environment should it escape the geologic repository. Under natural environmental conditions, plutonium solubility is limited by the formation of amorphous plutonium hydroxide, which you just saw, or polycrystalline plutonium oxide. That sounds good. Not only does Kd have a large absorption constant, it's not very soluble. All right, so we've got two things going for us now. Two things. All things considered, if plutonium escapes from a disposal area, it won't move very far because it's relatively immobile because of absorption and precipitation. Yeah, that's good to know. There are a couple low-level sites in, well, there's one in Illinois, for example, from many years ago, where they actually disposed of plutonium waste. And years of collecting shallow groundwater samples failed to identify any plutonium in solution. And that's one of the questions in the course I teach is, what do you think? Why isn't there any plutonium? And that's the answer. If it's there in solution, it probably precipitated. And if it's there in solution, it probably got absorbed very quickly before it migrated very far from the source term. Okay? Now, you with me so far? Isn't geochemistry fun? Huh? Great, great. Uranium has 16 isotopes. All of them are radioactive. Naturally occurring uranium, of course, you know, is about 99+% of U-238, about 0.7 235, and a little bit of 234. You don't hear too much about 234, other than the context of thorium as a fuel, but that's a lecture for another day. Uranium can exist in 5 oxidation states, 2, 3, 4, 5, and 6. Only the 4 and 6 are most stable enough to be of any practical importance, such as what we have in the real world. Now this is an interesting diagram. It kind of shows how complicated things like, uranium can be. What you're looking at here, this is pH from 2 to 10. And this is the percent species. Now in this figure, we've added stuff. We've added carbonate. We've added hydroxide. No, I mean, it's mostly carbonate here. Just carbonate, excuse me. Now you can see that under acidic conditions, most of the uranium occurs as UO2 2+, divalent cation. But as we get more and more towards a neutral pH, it goes away. It's converted to other forms. We have clearly emergence of uranium carbonate forms, such as this guy here. All right, 4- anion. So we're going from something that is positively charged to something that's really negatively charged just because of pH and because we've added carbonate to our system, which we could get carbonate if we started dissolving carbonates, naturally occurring carbonates like limestones. But as you can see, there's all sorts of other species. Here's your uranium hydroxide. It has its day, then goes away. And you have a lot of other minor peaks. So there's a lot of stuff going on here. I add this slide because the default KD for this guy is 50. You can kind of, I hope you get the feeling how crude some of these default KDs can be. And that you think a single KD is really going to explain all this? No, but it's a KD. Maybe just used for preliminary groundwater calculations, simulations, to get an idea about the mobility of uranium in whatever situation we're talking about. Tetravalent uranium is reasonably stable and forms hydroxide, hydrated fluorides, phosphates, all of which have really low solubility. They're not very soluble. Hexavalent radium is the most stable state, and the most commonly occurring is U3O8. Major compounds include oxides, fluorides, nitrates, fluorides, acetates, and a whole bunch of others, which are probably not all that relevant environmentally. Here's an EH-pH diagram of uranium. I want to show you this. This is one of my favorites. All right, again, pH and EH. If we go up to this field here, which is kind of in the neutral, or in between being oxidized and reduced, get a load of this now. We have uranium +2 in acidic media. We have uranium hydroxide monovalent cation under neutral conditions, and then we have a uranium hydroxide anion under alkaline conditions. So as we go from across the pH from something that is probably not very mobile because of the divalent cation, something that's intermediately mobile, to something that's probably very mobile, just because of differences in pH. Simple example why the pH of the solution matters. Now, under reduced conditions, uranium, the most thermodynamically stable form is uraninite, a solid phase. In other words, under reduced conditions, uranium would be thermodynamically more happy not to be in solution, but to precipitate. That's what uraninite looks like. I told you I was a geologist. Geologists like rocks. Fate chemistry of neptunium. Right. Neptunium solubility in water. At pH 7, ambient conditions, at an ambient pH, in a sodium chloride solution, it has been measured at about 45, 46 microgram per liter. In other words, it's not very soluble. Not a very soluble radionuclide. In soil, neptunium is generally mobile. As I'd mentioned before, the default KD is 0, but it is dependent both on pH and the oxidation state of the solution that it's living in. For example, at pH 8, I found a measurement of a KD on limestone, a KD of 215 liter per kilogram. I suspect it has something to do with reacting with dissolved carbonate, but I haven't gotten to that, back to that yet. Also less mobile under reducing conditions. Here's a pH diagram of neptunium, which kind of makes that a little easier. If we start with pH neutral, and right about here, typical ambient conditions, we see that the predominant form is neptunium oxide, a monovalent cation. If we go towards in the direction of groundwater, we have neptunium hydroxide. And then if we go into really alkaline conditions, then we have neptunium hydroxide in an anion form. And then there's a whole bunch of interesting little spices here, components. You can see it, we can actually have a 4, 3, 2, 1 charged cation in that little part of the diagram. But of course these would be under really acidic conditions that, well, frankly, you don't see those in natural systems very often. I don't think you'd ever see that solutions that acidic in a geologic repository. It would be interesting to try and explain it if you did. I have a feeling it would be because you had a lot of iron pyrite that was oxidizing, creating sulfuric acid, something like that. But by and large, I haven't seen too many examples where the groundwater was that acidic. Neptunium can exist in 5 oxidation states, 3, 4, 5, 6, and 7, but 5 is the most stable form. I like to show this photograph because 3, 4, 5, 6, 7 comes in different flavors. I like it, it has color. All right, the 4 principal, or fate chemistry of americium. The 4 principal americium isotopes, 241, 242 metastable, 242, and 243. Of course, 242 doesn't hang around very long. The known oxidation states for americium are 2, 3, 4, 5, and 6. The stable forms really are 3 and 4. And the most common state of americium is +3. Why do I throw that out? Again, it's good to know what are the common oxidation states of your radionuclides, because then you can put it in a context of how will that behave in the environment. Here's a EH-PH diagram of americium. It's a little simpler than some of the ones you've just looked at, but again, I want to point out that let's start with across the board here in a situation, in a part of the diagram that's neither too oxidized or reduced, that under in acidic conditions, the stable form is americium +3. All right, with a +3 charge, you can guess it probably will be retained by absorption. As we go towards neutral conditions, it occurs as a +2 cation. And then we come slightly alkaline as a monovalent cation. And then under alkaline conditions, bye-bye, it will want to precipitate as a hydroxide. Right? Not much going on with EH there. Americium isn't a big player in exchanging or losing electrons. Therefore, it doesn't really have a really strong EH type of chemistry, other than sort of some exotic things here, which are outside the stability of water. So we don't worry too much about those in the real world. Technetium. This illustrates what we were just saying with technetium. All right, here again, if we look at primarily EH, you can see under oxidized conditions, the most stable form of technetium is this guy, technetium oxide 4 monovalent anion, that mobile one, the one with the KD of 0. Under reduced conditions, it's happier as technetium oxide, C as in crystalline. No matter what it is, it wants to precipitate out, which reinforces what we were talking about earlier. This is a good example where not so much pH matters, but the EH does, the redox potential of the system. That is important here in this example. Europium. There's a radionuclide you don't get to hear much about, so I thought I would include it. There's not much to say here, though. Over much of the EH-PH field that is relevant to ambient conditions, it occurs as europium 3+. And in sufficiently alkaline conditions, it would rather precipitate as a hydroxide or a hydrogen compound here. So, but that would be pretty darn alkaline conditions. And like I said, for acidity in a geologic repository, it would be kind of unusual to find solutions with a pH that alkaline, unless there's some sort of sodium carbonate that's embedded somewhere, that's dissolving, that's adding hydroxide to the solution. But again, that would be kind of a site-specific investigation. But starting right off, it's not something you'd anticipate. Strontium. How boring is this? Strontium doesn't like EH chemistry, redox chemistry. It doesn't want any electrons. It doesn't want to take any electrons. And under the conditions imposed to make this figure, it doesn't do anything. Under the entire EH-PH diagram here, it occurs as strontium 2+. Period. That's all it does. All right. There are many, many more EH-PH diagrams that are available. They're really worth studying and becoming familiar with them, because you can just glean so much information quickly about many, many different radionuclides in solution. And that gives you an idea of what to anticipate. All right. Any questions so far? Excellent. Now, any questions so far? Excellent. Now, what I put on here, I tried to write big so that you can actually see this. So, I don't know how successful I was. this is for question 4. And I know from experience that if I don't tell you these things, I might regret them a little bit. All right. Now, question 4 is just an example or an opportunity to look at absorption of cesium by bentonite clay and something nobody has mentioned, no lecturers at all, desorption. Everybody measures adsorption, but nobody measures desorption. In fact,